I'll get started. Yeah.
Bu ders içinde kullandığınız scriptler bize available değil herhalde, değil mi?
They are. So I always put them on the website. So if you go to the course website, I just updated them this weekend, so they're nice and fresh. So for example, this is today's lecture, and under reading there is a Jupyter notebook. So if you click on that, and here's the notebook that I'm using today, and last lecture. And you can upload this to your own machine, and then run it. The convolution notebook probably needs a GPU machine, so you may have to set up AWS for that, but in general you should be able to download this file and upload it into Julia Box, for example, and then just go through the things yourself. So yeah, so this is so this is today's lecture. I'm gonna continue talking about convolutional neural networks, pooling, talking about fully connected layers versus convolutional layers and the representational equivalence between them. How does the backward pass work? The batch norm operation that's usually used in modern architectures. I'm going to show you an example of just like the multi-layer perceptron significantly improved over the linear model. We're going to see that the convolutional architecture is going to improve over the multi-layer perceptron when it comes to image processing tasks. And if you have time, this lecture or next lecture, I'm going to talk about more modern architectures and how do we understand what's going on inside the networks. How can we visualize the individual filters that are learned in, for example, an ImageNet type of model. Okay, so last time we sort of talked about the convolution operation, and we started with one-dimensional convolutions of a single instance, single channel, etc. And then we basically generalized that more and more to first multiple dimensions, then multiple channels, then multiple instances. And the full convolution operation that is supported in deep learning frameworks work as shown on the screen. So we have an X input image or batch of images that are each d-dimensional. D could be 2 or 3. And we also have 2 extra dimensions for channels and instances, CX and NX. Channels for images can stand for things like RGB. Channels for other applications might represent other properties measured in a certain location. NX is just simply the number of images in a mini batch. We convolve this X with a filter W. W also has D spatial dimensions, W1 through WD. Typically these spatial dimensions are much smaller than the full dimension of X. Doesn't have to be. The last 2 dimensions of W has to be CX and CY, which are the channels of the input and the channels of the output. So when you convolve these 2 tensors, you get Y, which has, again, these spatial dimensions. Each spatial dimension of Y is related to the corresponding spatial dimension of W and X in the following way. Here, P represents padding and S represents stride, which were 2 options to the convolution operator that we saw last lecture. And finally, the last 2 dimensions of Y are CY and NX, which basically here represents that the number of channels in Y is determined by the output channels of W. So that CY is the same as this CY. And the number of instances in Y is determined by the number of instances in the input. So that NX component does not change it as a result of this operation. So that's short summary of convolution. Anything you don't understand or do you want to remember? Yeah.
I guess so far we have not talked about layers.
Correct.
Just
So-
assuming one layer.
So this is just a single operation so far we talked about, and what we're going to do is we're going to insert this operation maybe multiple times into a network and build some model. But within this model, this convolution operation is going to be one of the layers, if you want to think about it in terms of layers. Okay. All right. So the next thing I want to talk about is pooling, which is another operation that are typically used in convolutional neural networks. Recently, maybe less so, and you will see why, because pooling basically subsamples the image, reducing its size. And you can achieve the same effect using strided convolutions or other means. So even though pooling was a standard component of earlier architectures, earlier meaning pre-2015, so things are evolving really fast, more modern architectures don't always use it. But let's learn about it anyway. So here's the pool operator in KNet. So it just takes X. There is no filter in this case, because we're just subsampling X, reducing its size. So basically what we're doing is we're taking an n by n patch in X, and then we're reducing it to a single pixel, summarizing the values in that n by n patch. Okay, so that's what pooling does. And summarizing here might mean, for example, taking the maximum value in that patch, or taking the average of the values in that patch. But as a result, for example, if we do size 2 pooling, 2 by 2 pooling on a regular image, what's going to happen is that every 2 by 2 patch is going to get reduced to 1 pixel, and that 1 pixel by default is going to contain the maximum value in the 2 by 2 patch in the original image. Okay? So there's some options, just like the convolution case. Window is maybe the most important one. Shows the window size, so we can get 2 by 2 or 3 by 3. Typically, the 2 by 2 windows are used. Padding has the exact same meaning as it does in convolution. So if you specify padding more than 0, we assume that there is a layer of zeros around the image, however many you put into the padding parameter. Stride is also the same as it was in convolution. It basically tells us how many pixels do we move from one patch to the next. Okay? The difference between convolution stride and pooling stride is the default value. In convolution, the default value of stride was 1. So we basically shifted the filter 1 pixel at a time, applying to the original image. By default, you can change that, of course. In pooling, the default is window size. So basically, after you summarize a 2 by 2 patch, you skip 2 pixels and you summarize a non-intersecting next 2 by 2 patch. The way that's it's normally used. And finally, mode is the other useful option, which basically tells you what kind of summary do you want. So default is max, so you get the maximum value in the patch you're looking at. You can use mode equals 1 for average of the patch. And there's another average option too. The difference between the two average options is whether or not you include the padded values, padded zeros in your average. Right? So if you have a padded image, so the inside is the original image and the outside is full of zeros. And I'm doing, let's say, 2 by 2 pooling, right? So my first window would be this 2 by 2 patch here, and here's maybe a value, 120. So do you want, for example, the average in this patch to be 120 or 30? Okay, in a sense, if we directly do averaging, we're going to get 30 because we're going to, all the padded values are going to give us zeros. But in a sense, that's sort of unfair because those padded values were just added artificially. So maybe you want to exclude them from your average. So if you use mode 2, you will get 120 for the average of this patch. Any questions? Okay. So let's do some examples. So actually, I'm going to have you do these on paper. So X is a one-dimensional vector that contains numbers from 1 to 6. What happens if you pull X? What's the output? Remember that the default window size is 2, default stride is 2, and default operation is max. So what is the output that you expect from pulling 1, 2, 3, 4, 5, 6?
2, 4, 6.
That's right. So it will basically take every pair of values here, right? And it will take the max. So this will give us 2, this will give us 4, and this will give us 6. So it's simple. Now let's play with the different options. So for example, what happens if I increase the window size to 3 in the same example? What output do I get? 3 and 6. Very good. And going back to the original window size of 2, but this time I'm going to use padding of 1. What output do I get? So, right, so let's, so here's the original X, 1, 2, 3, 4, 5, 6. Padding 1 means add a 0 to the beginning and a 0 to the end. And then the rest is default. So default means window size of 2. And I'm taking the max for each of these windows, so I'm going to get 1, 3, 5, and 6. Okay. Let's see if I'm right. Yep, 1, 3, 5, and 6. And finally, stride. So what happens, for example, if I use pooling with all default arguments, but I use stride equals 4, and my original input is the numbers from 1 to 10. What do I get?
2, 6, 10.
Right, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Since my original window size is 2, I'm going to start here. I'm going to get a 2 for the max, but since stride is 4, I'm going to actually skip to this window next. And 5, I'm going to skip to this window next. And I'm going to get 2, 6, and 10, skipping some of the pixels in the process because the stride is actually larger than the window size. Now here's an example showing the difference between the 3 modes. I'm going to start with my array 1 to 6, and I'm going to show the effect of 3 modes with padding equals 1. So when we say padding equals 1, the input becomes 0, 1, 2, 3, 4, 5, 6, 0, right? We're using window 2, padding 1, stride 2. So let's try to understand these. So the max is giving me 1, 3, 5, 6. The average is giving me 0.5, 2.5, 4.5, 3. And mode 2 average is giving me 1, 2.5, 4.5, 6. And to see why, we look back at this. As here we can look back at this example with padding 1, and these are the window sizes. So 1, 3, 5, 6 was the maximums. 0.5, 2.5, 4.5, and 3 are the averages if we count the zeros. And this last mode where we don't count the zeros will give us 1 and 6 in the beginning and at the end, with 2.5 and 4.5 in the middle. Any questions about the mode?
So,
Yeah.
was this method proven for computational efficiency?
There's several arguments for why pooling is useful. Basically, you start with a, let's say, 512 by 512 image, and eventually you want to basically come to a point where you're saying if there's a dog here or not. And the dog can be in various places in the image. So if we want some translational invariance, if we want to not care about exactly where the particular dog feature is, then pooling has that effect on us by reducing the image size we're working with, or in another way of looking at it is increasing the size of the receptive field of each of the neurons that we have, right? So every time we pool, a single neuron is now looking at a 2 by 2 patch. And if we pool again, that same corresponding neuron is looking at a 4 by 4 patch. So every time we do a pooling, we're basically increasing the effective receptive field size of the individual pixels. Yeah.
So if it's just the image recognition task, it makes sense. But if we have like an image caption generation task,
Mhm.
then it will not make sense, right? Because
You still want to summarize the image. I mean, presumably, if there's a dog and a cat playing in the image, and if they're shifted 10 pixels to the right, you still want to generate the same caption. You do want some translational invariance in your image output.
what I was thinking was like, in order to like talk about the relations between the images, shouldn't we like know where they are?
To a certain extent, yes. Of course, if you're basically generating descriptions that's saying there is a cat to the left of the dog, obviously if you lose all spatial information, you won't be able to generate that correctly. But then, do you really need individual pixels? Probably not. You might actually look at a much more coarse version of the image and still be able to give that information. Yeah. Yeah.
Does it have any aliasing effects, and do we actually what do we use for smoothing that effect actually? Because when you decimate the image like that, probably there will be some edge errors.
Right. So this is a question people typically ask before 2012, and hand-designed filters to counter those types of effects. But right now, we basically start with convolutional nets consisting of convolution and pooling operations that are initialized with random weights, and then we hope that the neural network training will learn the necessary filters to counteract any negative effects they have. So you don't actually do anything by hand when you're training these networks.
The network also will learn how to.
That's right. The network is,
overcome it.
remember, the network is full of filters. Okay?
Okay.
It's basically layers and layers of filters, and those filters are learning whatever the task requires. And if the task requires anti-aliasing, then they will learn.
Okay,
You know.
got it.
Any other questions?
So the pooling is not just on the first layer, it could be in the...
I'll show you a real example next. Okay, so now that we have our two operations, well, a couple more examples, I guess, do I have? Yeah, let me do a couple more things. So this was all in one dimension. What happens in 2 dimensions? Well, not that hard to predict. Instead of segments of 2, we're looking at patches of 2 by 2, and by default we're going to take the max. So what's the y that looks what's the y going to look like in terms of size and values after I pool this image. Yep. Right, so every patch, you look at every 2 by 2 patch, you look at its maximum, and that's what y is going to be. Okay? And finally, we should actually specify what happens with multiple channels and instances. Basically, pooling leaves the number of channels and instances alone, which means each channel and each instance is pooled independently. Okay? So the maximum of one channel doesn't affect the pooling result of another channel. Every channel is basically pooled within itself. So here's an example where I have 2 channels. So here's the first channel and here's the second channel. And if I pool this X, what I'm going to get is a 2-channel output. And the first channel is going to be the pooling of the first channel of X. And second is going to pool the second channel of X. And here we get the same answer for the first channel because the first channel is identical to the previous image. And here is the second channel, which basically pools the values in the second part of the X. Alright, so that's pooling. Now we're going to put all of these things together to actually build something. And here is a general definition of a convolutional neural network. Okay, you can use this definition to build most of the early models for convolutional networks like LeNet, which consist of a bunch of convolutional layers which contain 4 operations typically. I memorize them as CBFP. Maybe it'll help you too. So each convolutional layer consists of these 4 operations in that order: convolution, bias, the function, activation function, and pooling. Okay, this is usually ReLU or something like that. So that's the order in which we apply them. So you have a couple of these CBFP layers, and then you have a couple of weight and bias layers. So these are the fully connected layers. And then at the end, you give your prediction. So now let's look at the actual implementation in CovNet. So I basically decided to have all my weights and biases and filters to be part of this W array. Okay, so W array, just like when we were defining multi-layer perceptrons, we had a single W array that went weight 1 bias 1, weight 2 bias 2, weight 3 bias 3 for different layers. I'm going to do exactly the same thing for convolutional networks as well. And the way we're going to understand if a particular layer is convolutional or fully connected is from the dimensionality, right? So the weight array of a fully connected layer is going to be a matrix, 2-dimensional, whereas the weight array for a convolutional layer is going to be 4-dimensional because of the dimensionalities we discussed earlier. So this is what this guy is doing inside the for loop. So the for loop takes the weights 2 at a time, a weight array and a bias vector. And if the dimensionality is 4, then we know this is a convolutional layer. So I have a little dropout here, and then here's convolution and bias operations, and here is the ReLU and pool operations. Okay, so in the order that I gave, I first apply convolution to the input, then add a bias, then do a ReLU, and finally do a pool. Okay? Sometimes these two are switched because if you apply the F after the P, you actually have fewer values, so it might actually be a bit more efficient. And if the dimensions of the weight matrix is 2, then this is a fully connected layer, just like in the MLP. Again, after I apply dropout, I basically do the linear thing, okay? Wi times x, Wi plus 1, and I apply ReLU as long as this is not the last layer. The last layer I don't apply ReLU, I just output my regular outputs, okay? So this is a general definition for a convnet prediction function. So all I have to do now is actually initialize some weights, okay? And my weight array is going to determine which layers are convolutional layers and which layers are MLP layers. So before I show that, any questions about this piece of code?
So we have one fully connected layer here, right?
Actually, this particular piece of code doesn't care how many. So you can put as many convolutional layers and as many fully connected layers in your W array in any order you want. So this for loop will just process them two at a time and do the convolution thing or the fully connected thing as necessary. So what's going to control that is the weight array, which I'm going to show you next. So let's look at the weight array. Okay, so
May I ask a question?
yeah, of course.
We are using like any array or actually array type of
Yes.
structure, and when we want to actually work on GPU, we should use k-net array, right?
Only for the low-level numeric arrays. So
Okay,
when
then
you have
array
higher-level
construction.
structures like arrays of arrays or dictionaries of arrays, those don't need to be on the GPU.
Just the
because the-
operational.
Right. So the only things that actually enter the GPU operations are things like convolution or matrix multiplication. And whenever you have convolution or matrix multiplication up here, you see that convolution uses WI, matrix multiplication uses WI. So the individual components of W need to be GPU arrays, but W itself can be a regular array.
Okay.
Yeah.
Actually, when W itself is a k-net array as well, then we generally tend to have problems.
Yes, because k-net arrays are only defined for numeric values. You can't have pointers in k-net arrays right now.
The DNA structure.
Yeah. Okay, so we saw something very similar to this. I called it W init before. We basically use it to initialize a weight array given the size of the hidden layers. This is similar in structure, but instead of actually going through this code, I'm going to show you an example use. So here is an example use of how I initialize one of my models. So this model is actually called Lynette. It's from 1990s. It's the first commercially successful convolutional neural network model that was used to read handwritten digits from checks and documents. And the weight tuples, the dimensional tuples I give this Lynette initialization basically tell us exactly what needs to happen. So here what I'm saying is, first my input is going to be 28 by 28 by 1. That's my input size. The first number designates my input size. Okay? I don't have to specify the fourth dimension, which is the mini-batch size, because this model should work for any size mini-batch I choose. So the only things I specify here are the XY dimensions and the number of channels of my inputs. If I was working with colored arrays, then this last number would be 3 for the RGB channels. Okay? The last number is 10, and 10 designates the number of outputs I have, because I have 10 classes on MNIST. And the numbers in between basically tell me the type of layer and what size filter or weight matrix I use. So 5, means in my first convolutional layer, I want to use 5 by 5 convolutional filters, and I want to use 20 of them. Okay? So question, quick quiz. So W1 is going to be something like, what's the size of W, what's the 4 dimensions of W1 going to be if I want 20 filters that are each 5 by 5 applied to this input? What are the 4 numbers that go to the size of W1?
5.
Yes, that's correct. So 5, 5, 1, 20. And can you tell me why this is 1?
We are just using
That's right. So this is CX, remember? This is the input. This has to match the input channels. And this is the actual output channels or the number of filters. So there needs to be a 1 here. but I don't need to specify it for this initialization because I already know that the previous layer had one channel, so that doesn't need to be specified. All I'm saying is give me 20 5x5 filters. Okay. Following that, I have another 5x5 filter bank. This time I have 50 filters there. So what's the size of W2 going to be?
551, 50.
5, 5, not 1.
Ah,
Because at this point, how many channels do I have?
20.
20 channels. And how many channels do I have to output? 50. So that's the size of my W2. Okay. Now, next question. I have a 500 here, which basically means that I want a fully connected layer with 500 outputs at this point. Okay? So whatever the result of the second filter bank is, I'm going to straighten them out, right? I'm going to turn every instance to a single vector, no matter how many dimensions it has. It has 3 dimensions. I'm going to reshape it into 1 dimension. And I'm going to multiply it with some matrix that's 500 by something. So your question is, W3 is going to be 500 by what? Let's think again. So remember, what this W is going to multiply is the input size at that point. It's not multiplying the filters. It's not multiplying the W's. It's multiplying the X that goes through these W's. So you have, so basically, remember what we're doing. We're taking an X, and so let me summarize what we're doing. So we start with x0, which was 28 by 28 by 1, right? And then we say x1 is basically convolution, so W1 convolution x0. And then we add a bias. And then we add a ReLU and a pool. And
You haven't specified the pool.
we don't need to specify the pool because it's always going to be. So there's a ReLU here, and there's a pool here. Right? So this is going to be the first convolutional layer. And here's the second convolutional layer. So pool is always called with its default values. And W2 convolution x1 plus b2. Okay? And then x3 is going to be W3 times matrix multiplication of reshaped x2. So matrixed x2 plus some bias. So my question to you is, what is the size of this guy?
7 times 7 times 50.
So W3 is first of all a 2-dimensional matrix. So 7 times 7 times 50 would be 49 times 50. That's the wrong answer.
That's all the paddings.
Everything is default. So the default padding for convolution is 0. The default padding on pooling is 0. My convolutions are 5 by 5. Default stride for convolution is 1. Default stride for pooling is 2. Default window size for pooling is 2. You have all the information you need. So calculate the sizes of x1, x2. And once you have the size of x2, you will know what W3 has to be.
19 times 19 times 50.
Yep. Give me a single number. I can't calculate all the multiplications you're giving me.
No, you are asking second dimension.
Correct. So this is the output dimension. This is going to be the total length of x2 actually.
800.
Yes, 800 is correct. How did you get that?
I used the formula from the previous slide.
Okay, so what's the size of x1, for example?
24 by 24.
20 by 24 by, not 1,
I said 20.
20. Why 24? Because I'm applying a 5 by 5 filter to a 20 by 28 by 28 image. With the default stride and padding, I can calculate the dimensions of the output by saying original dimensions, subtract the filter dimension 5, add 1. Right, that was the formula. 28 minus 5 plus 1 is 24. But this is actually wrong because of the pooling operation here. What does pooling do? Reduces this half, so this is actually 12 by 12 by 12. Right? Okay? So what's the size of x2? Again, I'm applying a 5 by 5 convolution here, which turns this into 8 by 8.
And then 4 by 4.
And so 4, and then pooling reduces it down to 4 by 4, and then how many of them do I have? 50. So that's the size of x2. So the total length of x2 is 800, which is basically what this guy needs to be. And finally, I have W4 for the final output with 10 outputs. And what's the second dimension of this? 500, because that was the output of the previous operation. Okay, so let's check our answers. So I don't know if you can read the dimensions here. So the first K-net array is 5 by 5 by 1 by 20, as we guessed here. The second one is 1 by 1 by 20 by 1. What is that? That's the bias. The bias basically is per channel, so that's why it only has the channel dimension, not 1. So we're basically having a single number to be added to each channel as a bias. And then the next layer has 5 by 5 by 20 by 50, as we guessed here. And its bias is going to be 1 by 1 by 50 by 1. And finally, the next one is, as we guessed, 500 by 800 over here. And its bias is going to be a column vector of 500. Next weight, 10 by 500. And its bias is 10 by 1. Okay? Any questions about all this dimension stuff? Very good. So just to show you that this is actually working, so let's apply this thing and calculate the loss. So I basically picked the first mini batch from my test set, called it XY, and I calculated the softmax loss using my Lannett model, which I just initialized with this previous command. And the Lannett model applied to this XY with the convnet prediction function, which was defined earlier, gives me 2.3. And remember why it's giving me 2.3?
Log 1.
That's right, 2.3 is minus log 1 over 10. And since we randomly initialized everything, we expect the average probability to given to the correct answers to be 1 over 10, since we have 10 possible answers. And so 2.3 is a good one. So let's train this thing. Okay, so that was fast because I already trained it and saved it, and I had a condition there that if it's trained, just load it. If you actually wanted to train it from scratch, this is how long it takes on my K80 machine, so 230 seconds. I'd say that was a bit too long for the lecture. So, now, does anybody remember what the best result we got was with the MLPs on MNIST? What was our test set accuracy or test set error rate on MNIST?
95.
95? No. With the linear model, we were at 92%. With the MLP, we approached like 98%. With dropout, it improved a little more. At the end of the lecture, I actually increased the number of hidden layers to 256, hidden units to 256. And I think the last the best error rate we got was 1.5, so which is 98.5 accuracy. Okay, so we're going to compare the convolutional model with that. Here's the loss. So here, coming up from the top, is train and test of MLP, and the bottom two curves are train and test for the convolutional neural network. The first thing you should notice is how fast this thing converges. Okay, so when at this point, basically, finally, after about 40 epochs, the training set accuracy or loss of MLP is getting to be better than the test set accuracy of CNN. But basically, if we go all the way to the end to convergence, the training accuracy of CNN is already keep saying accuracy, is at 0. The test loss is 0.02, whereas the test of MLP never got below 0.05. Now, we may not have that much of a intuition about loss. Here's the error, percent error, which basically gives us a similar number, but these are typical numbers. Okay, so first of all, CNN comes down like crazy. You know, you train for 2 epochs, and it's already, you know, down below where the MLP is ever going to get in 2 epochs. Okay, so that's very fast convergence. Much less overfitting. Look at the overfitting of MLP. The gap between train and test, even though we're using dropout, is much larger. So much less overfitting with the CNN. And finally, the test set error is 0.5%. So we're at 99.5% accuracy on this task. Yeah.
Is this fast convergence because of the less number of parameters?
Actually, I was hoping that too, but it turns out in this particular example, the CNN has more parameters. But basically, its architecture is designed to take advantage of the symmetries in the problem better. Right? So basically, its feature detectors, the way things are connected to each other, the sparse connectivity, the weight sharing, etc., it all helps to learn faster. Remember, if you learn one useful filter in one part of the image, it's automatically applied everywhere else, right? With MLP, at every position you would have to relearn that filter. There's no there's no weight sharing in MLP. So in MLP, it learns to detect an edge on the left side of the number. It will have to relearn to detect an edge on the right side of the frame. Whereas if a CNN learns a useful pattern in one part of the image, that pattern is automatically searched for everywhere in the image, which might quicken the learning. So it's an architectural difference. Yeah.
Is this the case for also high frequency content images? Not like this low frequency content images?
Yes.
For the CNN?
Yes, because
ImageNet
ImageNet contains all sorts of different images of all different types, right? So this is only
successful. Okay.
Yeah. So I have an example with CFAR images, which are small, 30 by 30, but real natural images, and we see the same thing there. Yeah.
What do you mean by high frequency images?
Images where values change really fast, right? So in the MNIST case, you have a white background or black background, let's say, and then there is a white line, and then it goes into black, and there is very little change. Whereas if you look out to the leaves of that tree, there is a brightness change every couple pixels. That's a high frequency image. Yeah.
So here with 2 updates, we almost converge into
Not 2 updates, 2 epochs. Every epoch has 600 updates, right? So we have 60,000 training images. We're mini batching them 100 at a time. Every mini batch means an update. So after every mini batch, we do 1 update. So that means during 1 epoch, we do 600 updates.
So the objective function here, is it like has less local minima or something like that? Or?
the objective function in the weight space. Again, the problem is not, the problem that slows optimization down is not usually local minima. The problem that slows it down is all these, twisty turny. There is some visualizations of the weight spaces, a couple papers written on that we might actually get into, where they use dimensionality reduction to try to visualize the weight space in 2D or 3D. And then you generally see these very slow ravines. So let's say you generally see these types of shapes. Okay, so let's say this is a hole. In between two mountain ranges. So these places are high, and this particular channel is like a low river that I'm trying to get into. And one part of this river, let's say this part, is much lower than the other part. So what ends up happening is that, I start somewhere high above a mountain top here. SGD basically drives me down to the river base here. And then along the river, I'm basically constantly searching for the next thing, and I take a lot of steps, etc., and slowly improving, etc., to get to this low. And this takes a lot of steps. The reason being, the ravine here is a lot sharper. The gradients in this direction is a lot larger than the gradient along the direction of the river. The river is going down very slowly. So to discover that, when all the other dimensions seem a lot more important locally, takes a long time for these optimization algorithms to converge. And that's not the only problem. In the case of MLP, it did converge. Look at that. I mean, the training error is less than 0.1%. So it basically learned the training set. But still, you look at the test set accuracy, and it's high still. There is a lot of overfitting, in spite of the dropout that we used. Okay? Yeah.
Does pooling increase the performance?
Pooling increase the performance. Yes, if you didn't use any pooling or any strided convolutions, the input size would remain the same, right? So we would start with 28 by 28, and we would only go down to 24 here, let's say, if we weren't using any padding, and we would go down to 20. So our arrays would be much larger. So yes, in general, bigger arrays means more computational cost. But it's not the main motivation of using pooling. Pooling, as I said, is used mostly for translational invariance. So you want the same feature to be recognized no matter where it is in the image or within a certain range in the image. Okay. So back to your friend's question, weights. So how many weights do I have here versus how many weights do I have in the MLP, which was 784, 256, and 10. Right? So this was the input, this was the output, and this was my hidden layer. So somebody with a calculator or computer, compare these two weights, the total number of weights here. Okay, anybody doing it? You guys aren't curious at all? Which one? MLP?
So many 7,000 for
How did you get that?
calculation.
I know it. What did you multiply?
Those three ones.
Is that the number of weights you have in a multi-layer neural network? remember this multi-layer perceptron has two weight matrices and two bias vectors. What are the sizes of those matrices and vectors?
Showing the summation.
So the first weight matrix is of size 256 by 784.
200,000.
Okay, so this is about 200K, thank you. And how about these guys?
400.
400.
They're about 400K, yeah. But I'm pretty sure if I actually increase the hidden layer size here to match this other network, I would still get a similar result. I haven't tried it, you can take my notebook, play with it, add more layers, add more units. But I doubt that you can actually beat the performance of the CNN with any type of MLP. Okay. Now, this might give you the wrong impression that CNNs have some sort of magic that make them representationally more powerful. Just like MLPs, just adding these ReLU nonlinearities between these layers suddenly gave us this big boost compared to linear models. Are CNNs able to represent functions that MLPs cannot represent easily? Is that the problem? The answer is no. MLPs and CNNs are completely equivalent in terms of representational power, and I'm going to argue for that next using translation between matrix multiplication and convolution. Okay? This has other practical uses as well. For example, we can use fast matrix multiplication algorithms that were developed for linear algebra to do convolution, or we can use convolution in a fully connected layer to have some input size independence, etc. But let's see the equivalence of these two things. So here's our original 1D example when we first introduced convolution. My filter is just 1, 2, 3, and my input is these numbers from 1 to 7. And when I convolve these two things with the default settings, which basically is no padding, stride equals 1, etc., what happens is, this W gets swapped and gets multiplied with this guy, and then we shift it, etc., and we get this output 10, 16, 22, 28, 34. Now, this looks to be a very different operation than matrix multiplication. However, we can use matrix multiplication to implement it. There's at least two ways to do so. One, we're going to take our weight filter weights, and we're going to repeat them over and over again to form a big sparse matrix. Here's what I mean. So remember, our weights were 1, 2, 3, and we were actually going to flip them around to 3, 2, 1 before we apply. So I construct this matrix, and look at what I did. First of all, the number of columns is 7. Where is 7 coming from? The dimensionality of x, right? And the number of rows is 5, and where is 5 coming from? Dimensionality of y, the output. Okay, so since I'm going to do a matrix multiplication, one of my matrix dimensions should be the input, one of the other matrix dimensions should be the output. Okay, and then the way I fill inside this matrix is basically by repeating the weights in every row. Okay, so the 3, 2, 1, the flipped weights, I keep repeating, shifted by 1 in every row. Okay, and guess what happens if I multiply this W with x? I get the exact same result. Okay, so this is one way to implement convolution in terms of matrix multiplication. It's a bit expensive because I have to actually allocate a very big W, which is mostly sparse, and fill it in this way. There's another way. So instead of turning W into a y by x sparse matrix, I can turn x into a W by y dense matrix. And this is called the in-to-call operation. And it is actually used in current libraries to speed up the operation without wasting that much space. So what I mean by that is this. So remember, the original X was basically all the numbers from 1 to 7. Okay? And here, what I have is, 1, 2, 3, 4, 5, 2, 3, 4, 5, 6, 3, 4, 5, 6, 7. So this is the im to col operation, which is short for image to columns or something. I'm not sure. And the dimensionality of this is coming from what? What's 5? The number of columns. The number of outputs I want. What's 3? The number of rows. It's the filter size, right? So now I have a matrix here, a modified X matrix, that I can multiply with W, and I will get something of size Y. So let's try that. And I get the same result. Okay? So these are two different ways I could have implemented the convolution operation using a modified W or a modified X. Which basically tells you that in our Linnet model, wherever we see convolution, we could have replaced it with a matrix multiplication, a fully connected layer. Albeit with very sparsely connected matrix, sparsely populated matrix. But it would, if I had a large enough matrix, it could learn to simulate whatever this convolution is doing. But yet MLP has a very hard time finding that solution because of the representational issue. Any questions? Yeah.
If I had used the first model, then the backpropagation would fail, right? The structure would be changed.
Backpropagation would eventually fill those zeros
Yes.
with other things possibly. However, what I'm arguing for is that there exists a solution in the MLP space that can compute the exact same function as the CNS space. Whether or not your backpropagation would converge to that solution is a separate problem. It probably wouldn't, as we saw. Maybe we can force it by giving it a bias towards sparser weight matrices. But normally, it doesn't, unless maybe we have many more examples to force it to go that way. Yeah.
Is this used to compute the gradient of convolution operation?
I will talk about the gradient next. Any other questions? Okay. Now, we can also go the other way, namely implement matrix multiplication as convolution. So let me show you how, and then we'll talk about why. So let's come up with some sort of matrix multiplication. Here's my W of a fully connected layer. Here's my input X, okay, and here's my Y. Okay, if I multiply this W with this X, this is the output I will get. So the input size is 3, the output size is 2, fully connected layer corresponding to matrix multiplication. Of course, there's going to be non-linearities, etc., but I just want to simulate the matrix multiplication using convolution. So now I'm going to reshape W into a convolutional filter. Okay, so exact same numbers. Remember, W was something that went 1, 2, 3, 4, 5, 6, arranged into a 2 by 3 matrix. I turned it into a 3 by 1 by 1 by 2 tensor. Same numbers, just reshaped. Okay, and I'm going to have to reshape x2, which was a one-dimensional vector, into a four-dimensional tensor for convolution, just by adding extra 1 dimensions. And if I just use the convolution operation, notice that I get 22 and 28, which is the exact same result that I had here. Okay, so basically you can go the other way as well and implement matrix multiplication in terms of convolution. Now, why would you ever want to do that? One interesting property of convolution is that it will work for any input size. Okay? If I have a 5 by 5 by 1 by 20 filter bank, I applied it to a 28 by 28 by 1 input. Did I have to? No. This could have been 100 by 100 by 1 input, or 200 by 200 by 1 input. Okay, as long as the channel numbers match, I can apply this W to any size input whatsoever. What would change? The output size. So if the input size got bigger, the output size would get bigger. Okay? But let's look at the linear layer. the fully connected layer. This one has 800 inputs and 500 outputs. So if I apply it to a vector of 800, I'm happy. But if I try to apply this to a vector of 801, I get an error. Okay, dimensionality mismatch error. But if I convert this operation into a convolution and use it as a convolution, then if the dimensionality of x changes, I don't get an error. I just get a result that's bigger than I expect. Okay, so that's one possible use case to create these fully connected type layers that are actually more flexible in terms of their input size. But the more important point of view, by the way, here's my calculation on the
Can you repeat the last part?
200K, 400K. Okay, what would you like to repeat?
When you add one more, you get bigger value?
What happens in convolution, if I convolve these two things, I get a 24 by 24 by 20 image, right? If instead of 28, I start with 30 by 30, what would I get? 26 by 26 by 20 image. So if I grow the input, the output would also spatially grow. It wouldn't give me an error. So this particular W does not expect a input that has a certain spatial size, right? So I can use that property to possibly create fully connected layers as well that don't get destroyed when you have a variable sized input.
Sorry.
Yeah.
Is this something purely theoretical, or is it an actual practical issue?
I haven't seen an actual practical model that uses this, but I don't see why you can't use it for an image. So I could possibly imagine something that's trained on 100 by 100 images to recognize dogs, for example, but then you get 1,000 by 1,000 images and you can just deploy this thing like a filter if everything was written in terms of convolutions, and it would still work. So number of parameters in the MLP example was 200K, and number of parameters in the LANET was 430K in this case. But even if we actually play with those and change them, I think the results would be similar. Okay? All right, so somebody mentioned, I want to do two things before we go. Let me start with the more important one. So let's look at one operation that I basically did not mention is batch normalization. Now, batch normalization is a relatively new operation that improved the convergence properties of these models a lot. Right now, any deep ImageNet type model uses batch normalization layers between these convolutional layers. So one of the problems with optimization is when our initial values for the weights are in a certain part of the space that's not very nice. Maybe they generate a lot of negative values when multiplied with the input, which get mapped to 0 by the ReLU, and then we lose our gradient. We don't know which way to go. Or, you know, it's hard to figure out what the initial values should be, or what the ideal output magnitude should be in the hidden layers. Okay? So batch normalization takes the guesswork out of this problem. It makes your training much less sensitive to initialization and optimization parameters. So let's say we have a mini batch B that contains m examples of x. We're going to think in terms of a fully connected layer here, let's say. And what batch normalization does is basically takes all these x's and transforms them linearly to have 0 mean and unit variance. Okay? So it's just like normalizing your input numbers for a regression. You subtract the mean, divide by standard deviation to make all the values 0 mean and unit variance. Okay? So I calculate the mini-batch mean over here, I calculate the mini-batch variance over here, and then I calculate these alternative values x hat, which are normal. Now, if I add this in front of every layer, what's going to happen is that the activations between every layer are always going to have the same statistical characteristics. There will be numbers between -1 and 1, you know, generally, but with zero mean unit variance. Forget about the -1 and 1, that was wrong. Okay. In addition to this, though, your problem might require these numbers to be distributed, you know, differently. Maybe the standard unit normal distribution is not the right thing between layer 2 and layer 3. So for each batch normalization layer, I also learn two parameters, gamma and beta, that linearly shift and scale these normalized numbers. So I'm doing two things. I'm taking your arbitrary distribution, first normalizing it to normal 0, 1, and then shifting and scaling them if necessary. So that's the batch normalization layer. And the only two parameters I need to learn are these two things, and I can actually calculate the gradients for them and optimize them just like I optimize any other parameter in my network. Yes?
Two questions. How do you know it's normal? Like we are transforming it to something with 0 mean and 1
Right.
unit variance, but how do we know it's normally distributed?
It's not.
Okay. And in the scale and shift part, aren't we just so we have first
Normalized it.
Yes.
And
Now
then-
we're just adding it a mean and a variance.
Correct. But notice that we're not going back to where we came from. So let's say
Yes, we-
the original input data, its distribution had, you know, 100 mean and 200 variance. Okay? But where it has to be in order for learning to happen easily is maybe, you know, 5 mean and 2 variance. Okay? So I achieve that in 2 steps. I first map whatever is incoming to 0 mean and 1 variance, and then I shift it to the appropriate location for the learning algorithm to proceed.
Those two parameters, the mu mean and mu variance, are
Learned.
learned, and they are different for every layer.
Correct. Yes. In between every layer, we would have a batch normalization layer that learns its own 2 parameters like this. Yes.
So instead of introducing 2 new parameters, wouldn't I be able to adjust it like with my weight matrices, like by scaling them?
Yes, you could achieve the same effect. However, that doesn't mean that you can learn in that range easily. So maybe your numbers are too big. Since your numbers are too big, your weight numbers become too small, and that makes their gradients too small. And, you know, basically floating point approximations become a problem. But basically you start seeing when you start playing with these models that initialization actually matters. So instead of initializing all my W's with, you know, standard normal 0.1 times 0.1 or something, if you initialize them with standard normal 10, you will see that the optimization will go all over the place and the gradients will be too big and I'll have to adjust my step size accordingly, etc. This basically makes everyone behave much more predictably. So you don't have to worry about the exact magnitudes of the weights and the gradients when you're first starting the normalization. And we've actually, in the lab, experienced a lot of models which basically converge if you use batch norm, but doesn't converge if you don't use batch norm. I'm sure that there might be a way to tweak it and initialize it just right, so it would, but it takes too much effort, and this is much easier. Yes?
Why do you do it on batches, not the whole data?
So during training, you do it in every batch. So you take every batch, you calculate the batch mean, batch variance, and then normalize things. Okay? During testing, though, remember, during testing, I may not even have batches. Somebody might give me just a single instance and say, you know, process that single instance. Then how am I going to know what my mean and variance are, right? So typically what's done is basically during training, I also learn an approximate value for mu and sigma squared from my training batches, and during testing I freeze them. So during testing I don't do the first two steps. I use the mu and sigma squared I learned from the training set. Okay? So in addition for every batch norm layer, in addition to learning the ideal values for gamma and beta, I also learn the average mean and average variance, or the, you know,
From
Yeah.
training data?
from the training data, yeah. So that
Right.
during testing, I don't need to calculate batch mean and batch variance, the first two steps of this process.
So when we're using mu and like sigma for batches, do we have improvement over when we use the mu and sigma of the training data?
I don't think the difference will be that great. So if we actually went through the whole data and learned all the mu's and sigmas, but the thing is, okay, so the mu and sigma of a later layer will depend on the gammas and the betas of the previous layers, right? So if you're in the fifth layer in the network, from the input, you went through lots of convolutions or fully connected layers, and after each one, you did this shifting and scaling thing. So the inputs that come to you, the statistics of those inputs are affected by what happened before you. So how would you actually measure that for the whole training set? What would that mean? Would you freeze all the gammas and betas for all the layers and then calculate some statistics? And then,
Here, for each mini batch, do we calculate a gamma and beta? Like instead of one gamma and beta for the whole training set?
okay, so there's four things we're calculating here. The mu and sigma squared, the first two steps, are calculated for each mini batch. Gamma and beta are parameters like W. They're basically updated every time we calculate gradients. So we actually calculate gradients with respect to gammas and betas as well, and optimize them. Okay? Any other questions? Yeah.
And do you use it after every layer, or is there some convention?
That depends on the architecture you're using. So next lecture I'm going to talk about various modern architectures. But yes, generally the idea would be, for example, in this simple Linnet case, I would put it after every convolutional and fully connected layer. Okay, one last thing I wanted to show you. Before I let you go, I have 1 minute to talk about backprop. So I have no time to write, but I can show. What happened? Did it crash? No. Okay, that saves you from the backprop torture. But it's not that big a deal. So if you look at it one dimension, oh, it's back. It's back over there, but it's not back over here. Oh. Sorry about this. Is that backprop? Yeah. I don't know what I did. Okay. This is all I wanted to show you. So let's say we have a one-dimensional example, x1 through xn, and we have a W filter, and we're using no padding, stride equals 1, etc., regular convolution. And let's not even flip the W's, let's use the cross-correlation mode. That basically works without flipping the W's. So how would we calculate the output Y? The output Y would be basically the result of a bunch of multiplications and additions, right? So y1, for example, the first value in y would be x1, w1, x2, w2, x3, w3, etc. That product. And then y2 would be shifted one. So you would be doing x2, w1, x3, w2, etc. And every y would be basically a certain product, dot product of w's and x's. Okay? So what that means is, and now let's say in the back propagation, what do? I'm interested in the backward pass. Backward pass means what? If I have an operation and somebody tells me the error sensitivity with respect to the output of my operation, I need to figure out the error sensitivity with respect to the inputs to my operation. So in other words, I calculate y equals convolution wx. I go forward, I calculate the loss. In the backward pass, somebody tells me delta j, delta y, which is basically the error sensitivity of each of my outputs. And from that, I want to calculate the W sensitivities. Okay? So now if you look at these equations, W1 appears in a lot of different lines. So that means it's affecting the output through all of these different lines. So the gradient with respect to each of these uses have to be added up. Right? So here, in the first case, W1 is multiplied by x1, and the resulting y1 affects the output somehow. Here, the same W1 is multiplied by some other number x2, and the resulting y2 is basically affecting the output. Okay? So, coming back, we can summarize the effect of W1. W1 prime is basically the derivative of the loss with respect to W1, let's say, as x1 times whatever y1's effect is, x2 times whatever y2's effect is, etc. Okay? So this is basically an application of the chain rule. Did I lose everyone? Okay? It's all clear? All right. So if you believe me, then you also see that this is another convolution. This is basically the convolution of x with the gradient of y. Okay, so basically the long story short is the gradient of just like the gradient of a matrix multiplication can be computed by another matrix multiplication, the gradient of a convolution operation can be calculated using another convolution operation. Okay? So there is no magic, it's a bunch of additions and multiplications.
Is it because of convolution operation? Something Is it because of linearity of convolution operation? Something else?
So do you want me to say something in general about
Yeah, I'm trying to imagine actually the transition from that.
I don't know in general what, which operation families go together, but for example, the gradients of all the trigonometric operations are other trigonometric operations, the gradients of, matrix linear algebra operations are other linear algebra operations. We should ask a mathematician why these groups, why these families like each other so much. Okay. Don't have a ready answer. All right, see you next time.